Let's get into linear bearings a little bit. And I'm going to start with, I'm basically going to move you through the different technologies and hopefully show you what kind of bearings you could use in these different, we're using bearings in different places because there's motion involved. So what are your choices as to the actual bearing that you choose? Strengths, tolerances, speeds, accelerations, lubrication, environment. There's a lot of choices when you go to choose a bearing, but I'm going to narrow it down to some of the more common ones that you would use in a motion system. First thing, when we're talking about rotary bearings, I kind of think I don't need to cover much of the rotary bearing. There will be a few times when we discuss something here and there, but in general, when you think bearings, you're already thinking, oh, it's a rotational bearing. And then it's just a matter of how do you mount it and what are the tolerances of the shafts, and is it a slip fit or a press fit? Should you glue it on? There's some basic bearing things that hopefully you've had a chance to build something. Building things, there's really no good substitute for getting your hands on a bicycle, skateboards, anything with bearings, and having to maintain it, build it, fix it, something like that, because that's the only place you really learn this stuff in the real world. I got lucky, and I don't know if you call it lucky or not, but I grew up on a farm. And so, I grew up around dirt and bearings and a little bit of welding here and there. And so you just kind of get used to these kind of things. If you're not used to this, find a project, build a drone, build an RC car, and look and see how the bearings are put together. And there's just no replacing experience for knowing what to do with the rotary bearing. However, you get very little experience in the real world with linear bearings. And so I'm going to spend most of my time talking about linear bearings, linear bushings, and bearings. So first thing you notice, I delineated the difference between a bushing and a bearing. Bushing means there's sliding friction. Bearing.
Why is it that linear bearings are not used as often in the actual world, as you put it?
Well, they are as soon as you go to automation and you're trying to make something move in 3D space. I guess it's a good question. In general, when you try to move things around in 3D space, there's two coordinate systems. There's polar and there's Cartesian. So you learn both of those in like 3rd grade or something, maybe 7th grade. Somewhere, but you have two choices to find a point in space, polar and Cartesian. So from a calculation standpoint, moving something in 3D space, if you have only polar coordinates, if you have rotary axes and you're doing, this is basically robotics, is all polar coordinates. And the difficult thing about that is that you've got, if you want to actually program this point here to move a straight line in 3D space, your programming is all in polar coordinates. So you have inverse kinematics that you have to do if you want this point to go in a straight line. It's really easy to make something go, for instance, let's say you had an arm and here's your motor. This point right here is really easy to make it go in an arc some distance, right? But to have this point actually move in a straight line for some reason over to this point means you're going to need an extra pivot point, and you're going to need some combination of two different motors moving together to actually get straight line motion. Why would you want to do that? Well, let's say that you had a conveyor, and you're asking the robot, this robot here, this is Mr. Robot here. Mr. Robot is you're asking it to come over and pick up some object, and this conveyor is moving in a line. This point of the robot right here, at some point for some period of time, needs to move along this axis in a straight line. If you're doing all polar coordinates with your motors, that's difficult programming. And that's graduate level, that's inverse kinematics. That is robotics design, and they'll spend a whole semester just on the math to do that. Or alternatively, you can just buy the math. And that's what I would do, is I would go buy the math from a robot company, basically meaning if you're going to build your own polar coordinate mechanisms, then go buy a controller where you can put in the distances, where you can put in the distances of each arm, what you want them to do, and you buy the kernel that does all the inverse kinematic calculations, so that you can simply program to go from this point here over to that point there, and the controller the robot controller that you buy does all that math for you. So the modern world, pretty much, even if you guys go and you design a robot for, you know, a special purpose, you're probably going to go buy the control package and match the variables up and have it do it for you. Doubtful you're going to be writing your own code. Similar to how you used Excel stepper to run the stepper. You didn't go start writing code at the very base level. You grabbed a library. But that one was cheap. Robotic controllers are probably going to be a couple $1,000 to do that. So I'm getting Roger, I'm still answering your question. So why linear? Because all that stuff was actually hard. Think about, though, as soon as you have, again, let's say you have an X and a Y motion, and you want to do some particular, let's say you wanted to even do that move. Well, you know that if you wanted to do that move, then you have a motion profile, and the motion profile has linear elements to it. Thus, you can use kinematic equations to calculate acceleration, because it's final velocity, initial velocity, time, and distance, right? These, you know, the standard things. So it's really easy to do the calculations for constant accelerations using kinematic equations. And those translate, if you wanted to do this movement here on an angle, then this might be X, and then you might have Y doing, the big hardest thing you would have to do is match up these breakpoints. Y could be doing some motion like this. It might be doing this. You know, maybe it's going much faster because you're moving more along this axis than you are this axis. So this motion profile might have a higher velocity than this one. But when you put these two together, you get an easy linear move. Even easier is just asking one axis to move in that axis. So I guess the bottom line is Cartesian coordinates are way easier to do programming in. You can do any of the math. It's a simple motion profiler. So turns out that we say, oh, you guys are mechatronics. What do you tell your friends when you say, they look at you funny, you say, I'm a mechatronics engineering major, and they look at you like, mechatronics, you know, what's that? Or motion control or machine automation. And so what do you end up saying? I mean, I can do this with my parents. I don't know if they even know what I do, right? And it's like, oh, robotics. I teach, you know, first of all, I build robotics modules for companies. And now I say, I teach robotics at Chico State. Oh, you teach robotics, right? You know, and then the difference, the subtlety for you guys is I'm teaching you not how to run the robots and how to design conveyors. I'm teaching you guys how to actually build the robot. To me, that's the level of the mechatronic engineer. Is I'm teaching you all the stuff to actually build the mechanism itself, and as opposed to the automation and robotics major, which some of you may want to do. Used to be sustainable manufacturing. Now it's changed a little bit, but they are more in the implementation of a robot, which there's plenty to do there to get it right in terms of grippers and deflections and accuracies. But this is where we're going. So back to why do I need to teach linear bearings? Much smaller subset of people that are actually designing linear bearings into something. If you went out to a processing plant, like I grew up, we had a walnut farm, and we had a hoer and dryer. And so we had conveyors and we had augers and we were moving things around. I don't think there was a single linear, but everything that we moved was rotary bearings and then belts or chains and more rotary bearings. And they're fairly simple to keep the dirt out of them because you can put a seal on it. And so in the world around you, you know, cars or, you know, there's not I'm trying to think of the single linear bearing in your car, maybe your seat, but that's probably not a bearing. It's probably a bushing. Where else is there a linear bearing in your car? Everything's rotary, all the axles, everything holding the gears. I can't think of it. So it's not as common is the answer to your question. But I'm glad you asked because it brought up a good point that we want to get into about general machine design. Which way are you using, Cartesian or polar? Okay, so before we got sidetracked on coordinate systems, I was kind of going over linear bushings versus bearings, which means generally rolling friction, meaning generally little ball bearings. Okay, can everybody see? Go back to this other view here. This is going to take me a little bit of work around. Okay, I'm going to be mainly focusing on the camera, I think, at first. And instead of drawing out all these things, hopefully I'll be able to show them on the camera what I'm doing. But I'm going to talk about first the different kinds of sliding bushings that maybe you will use in certain designs, and maybe you will think about using them and move on to something else. You know, our big overriding, you know, mu sub S and mu sub D. These are what we're really thinking about as you begin to design bearings, in addition to how much load they can carry and that kind of stuff. So let's first go to a couple different bushing types. Let's go to one that you're already familiar with, which is a UHMW, or sometimes it's called Delrin bushings. You guys have been exposed to these kind of bearings in Mech 140. You may remember this little device. This went in, you had, oh boy, try and dry it. When in 140, you used aluminum extrusion. I think it was Bosch size 30 or something that you use for the most part to build machines. Probably if you guys have already done 440A, you're probably thinking about aluminum extrusion as a very flexible type of machine framing, because it's not welded together. You can bolt it together, and then when you find out your mistakes and your add-ons and feature creep that happens, you can go back and change it. So there's a real specific reason that we used aluminum extrusion to build machines out of. This design element here went into, let's see if I can even draw this, had some sort of, you know, it has some sort of thing like that, and then some slot in the extrusion, and same thing on the other axes. And then you would have put this bearing here, would have gone into that and would have gone something like this. this would have been the bearing design essentially. So that's me trying to design, if you look over the camera, that's me trying to design that little piece of Delrin. And in this case, the sliding surface, if you loaded it down with some sort of load, then you saw friction here, here, maybe it was shared there a little bit. You could put some moment loading on it, but you were really dealing with the sliding friction, which is classic static friction and dynamic friction. And I think that the frictional coefficient of this dynamic was about 0.17, keyword being about that. So, it worked pretty good when there wasn't load on it. And then if you did put load on it, either, if you put on some sort of even dynamic or moment load on it, then you really started to have it dig into the corners. And you also had one other problem with the sliding friction, which was you would get binding. Binding happened on these sliding bearings where the surface, if you looked at it from, over, let's say here's the size 30 stuff, and then the actual bearing was here, and moving back and forth. What happened was, so this is supposed to move this way, right? What happened was I drew this yellow line and it kind of looks straight. What if I kind of did this though with it? And I said, yeah, in reality, that's probably more what the surface looks like if you were down measuring thousandths of inches. And so this large surface area here ended up being somewhat of an averaging effect. It ran across the high bumps, so to speak. And the longer you made this part here, the longer distance, the more it averaged out the bumps and the more accurate its motion became as you went back and forth. So these were useful, but in order to, the trouble with this, this undulating surface is that if you want to avoid binding, you have to have parts of it where you have play. If you want it not to bind in some, it's going to have a changing amount of free play to avoid the binding spots because the surface wasn't perfect along here. And no surface is perfect. So to some extent, you always have this issue. It's an issue that you're always going to deal with, which is what's the mounting surface like? Or even worse, this extrusion, when you just go by aluminum extrusion, it's actually a terrible thing to make bearings out of because you would like to have the bearing manufacturer tell you how flat is this? You'd like to have some sort of flatness spec. And when you go to try and find the flatness spec for the aluminum extrusion from Bosch, you look and you look and you look, and it doesn't list a flatness spec. It doesn't list anything related to flatness. And that's always a big clue when you don't see a spec that you're really after, that you're using it wrong. You were after a spec for flatness because you were trying to make a bearing out of aluminum extrusion. And they don't give you one. And when you come on, it's like, well, we really never meant that to be a bearing. And then you ask them, it's like, why is this in your catalog then? Well, it's handy, you can move things back and forth, but it just really slides, and it's not really a great bearing. Because remember, the whole idea of this bearing is we're trying to hold some part out here that's attached to it. We're trying to get this point right here in 3D space to be predictable and move back and forth. And the trouble we have with everything is that's your goal, is to make that point move. But what do you have to do to make it move? First of all, you have a distance here. Then you have an attachment point here. So there's deflection there. You have the opportunity to do this. It doesn't, is your 90 degrees perfect? Then this moves back and forth. It moves back and forth here. And finally, you get back to the point where you're going to attach, after all that, you get back to the point where, okay, now we're got to here. Here's where we're going to attach the motor, coupler right in here. Here's where the motor will go. Maybe it's a motor like this. Maybe it goes click. There's the motor, but still, you're not, the thing that you control isn't even this motor shaft. All you get to control is the windings that turn on in this motor. And so there's not even contact between the motor's windings and the rotor that moves it for you. So you've got this system where there's several things that happen before you finally get out to the very end, which is moving that point in space. And so this is where robotics manufacturers have a very difficult time dealing with any sag in a bearing this way makes this out here sag. The whole dynamic loading and deflection of a robot, getting rid of backlash in these elements is really difficult. So the people that are making accurate robots, they're on like version 35 of their robot. And every time they've worked a little bit on, let's stiffen up this part of it. Let's get rid of a little backlash here. And at the same point in time, they're trying to hit a price point. Well, here we have a price point of 30 cents. So it seems really ideal, except for the static friction is really high. Now, why does that matter? It matters. I'm going to introduce something right now called stiction. And this is going to carry through all of our discussions. It's a term, there's no official thing called stiction, but it's a term that all linear bearing manufacturers will use it. And what it is it's the difference between, it's what happens when you go from static friction to dynamic friction. Let's say that I decided I wanted to move this point here. I want to move this is point A, and I wanted to move it to point B. And the actual move, we're going to go A to B. Let's say I want it to be 0.002 inches, 2/1000 of an inch. So roughly I want to go, what's a piece of paper? The width of a piece of paper is 2.5 thousandths or something like that. So we're going to go the width of a piece of paper. That's how far we want to move. By the way, 2/1000 of an inch is a huge number. That's almost not precision mechanics. That's almost just anything. 2/1000 of an inch. Call me when you get times 10 that. But let's say you wanted to move to 2/1000 of an inch, and you had friction. What happens when you're trying to move? What can we move around? What can you push on your desk? Find something on your desk that's just sitting there, and then I want you to move it 2/1000 of an inch. So I'm going to move my iPad. Let me get a better example here. Let me find something. Okay, here we go. Here's an example. So let me ask you a question. Do you guys prefer me to hold things up like this? Or would you rather have me put it under the camera and do that, and move things like this?
Probably easier on the camera because there's 3 screens otherwise.
Okay, so let's stay on the camera.
Under the camera.
Let's stay on the camera. So here we have a linear motor. By the way, this is a linear stepper motor. Not all stepper motors are round. So just as an aside, since we've got it here in front of us, I have to be real careful when I pull this off because there's huge magnets in here and I don't want to get them too close to any sensitive electronics. I don't want to get them close to my iPad, my phone. What else I got? I guess that's all I got going here. So I'm going to move my iPad over a little bit. All right, so when I pop this off, there we go. So this is a linear stepper motor. And you can see the teeth, the tooth structure here. This is where all the magnetics are. And there's a tooth structure right here built into this conductive bar of steel. And there's some bearings that, these are little roller bearings here. Can you see those? Little roll bearings that roll along this surface and give you an air gap. And then these bearings here, these little roller bearings are moving along the sides. And so they're carefully controlling the air gap of this. I'm going to put this back on now. That's how it goes first. And then you always got to be careful when you're dealing with motors, not to get your fingers pinched when it goes together because they're really strong magnets. So now my goal is I want to move this thing here, which has some friction to it, pretty low, but I want to move it 0.02 of an inch. So what do? I start to put a little bit of force right here. And my force it's non-zero now. I'm pushing, actually. It's non-zero, 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 non-zero. Oh, see that move? So let me actually mark this. So I'm going to try and make a move. So I don't know if you can see that point. See that line? You see that line? Yeah. Okay. So there's the line. Let's move this up a little bit. So I'm going to try and make this move. There's the line right there. Okay, it's lined up. It's right on the line. Right there. Now I'm going to try with my finger, I'm going to start to apply force. And this has a static and a dynamic friction. So when I apply force, right now it's 0 because I'm not touching it yet. But as soon as I come and I start to touch it, now the force is non-zero. It's not even deflecting my skin yet, but I'm gradually increasing the force. Oh, there it is. It moved. Darn it. That thing's, okay, let me do this again. That was a huge movement, right? You see this? So here I am. I'm trying to make this motion. Let me draw it over here so you can see a little bit better. Okay, so there's my motion. I'm going to try and make this move. I can't make it move less than 1/16 of an inch. So what happens is when you have a large differential between the static and dynamic friction, the result is that you can't do 0.02 of an inch with that push, or you have to wrap other controls around it. I can't physically make this move. Even 0.02 of an inch is nothing. I can't make it move 0.02 of an inch because as soon as I move it, my human control is so bad that unless I'm actually doing microstepping and controlling this with magnetics, which then you could do microstepping and then you could get it to do that. There's a big difference, and it's hard to do small moves when you have a large friction. So one of the goals of machine design is to remove friction, because one of the goals typically is to do small motion. You had a resolution of your stepper motor. What was the resolution? Your motors had a resolution. You had, oh, well, you guys, some of you were 10,000 steps per rev, something like that. That was your resolution. Okay. News flash. You never did a single microstep in your microstepper. What happened was you had some friction in the bearings, not much, but you had a tiny bit of friction. And as this moved, as the rotor magnetics moved 1 microstep, the rotor itself didn't necessarily move 1 microstep. It started to feel the pull, the magnetic spring was starting to pull it. But if there's a tiny bit of friction in here, it didn't move. You give it 2 microsteps. Now it's starting to extend that spring a little bit. 3 microsteps. Somewhere around there, maybe 4 microsteps, it went broop. And it actually, the smallest resolution that you could, this is programmable, or you could call it theoretical. So you say, oh, microstepper motor, I could make that thing move 1/10,000th of a revolution. If we had better gauges, if we put an encoder on it, or we had some sort of, maybe you even put a, and I've done this before, you put a laser pointer on, you wrap a laser pointer on the shaft, and then you point a laser pointer over here at the wall, 20 feet away. And then you do 1 microstep of this motor, and this doesn't move. 2, 3, 4, finally, it moves up to this spot. And that then is, this was theoretical, the smallest, your resolution. And then this was actual. And why is there a difference between theoretical and actual in terms of resolution of the system? Because there's friction. So one of your big goals, if you want to make small motions, you've got to get rid of friction. There's just no way around it. You've got to get rid of it. So pretty much the sliding friction of this value, 0.17, nah, that's bad. We don't use that much. Oops, somehow I erased it, which I'm just gonna go, that's bad. That's terrible. As an example, just so you know, while we're on that subject, if we put in a linear bearing, if I put in this bearing here, and these are rolling linear bearings, the actual friction, coefficient of friction in a rolling ball bearing is, instead of being 0.17, the rolling is probably closer to 0.0015. So this is sliding, is 0.17, rolling a ball bearing is tiny. And that's why we're going to use linear bearings, not linear bushings. But it's worthwhile to kind of go through, start at the bushing level, because you're always tempted to start there because they're so cheap and they're easy to make things move back and forth, especially with UHMW or Delrin, very common material. And we made you use it in 140 as your bearing. That was your bearing. And yeah, we're kind of in the back of the room going, yeah, this is really bad, but at least you could design something and you didn't know any better. All right. There is worth mentioning one style of real world frictional bearing that's lubricated, steel on steel. You would think it's the worst thing ever. So here we have, let's see if I can get this back. Okay, so here we have, this thing here is called a dovetail slide. Oops, let me change that, hold on. Dovetail. And there's a variation of it that is a little different. So this dovetail, if you look at the structure of it here, you'll see that it's basically got this kind of top to it, and then the bottom would look like this. So you'd have a bottom that goes in here. And I'm going to stop short over here on purpose. So top and a bottom, that's this and this. But I drew this specifically short. If you look right here on the camera, hopefully that's showing. There's one more thing. When you have this kind of bearing structure that's sliding friction, the one thing that you're going to have to do is you're going to have some way to adjust preload. Any bearing you do, whether it's rolling or sliding, one of the things you're going to have to deal with, and I would ask you if I was doing a design review with you, okay, you drew that bearing in there, how are you planning to adjust the preload of that bearing? And what I mean by preload is that difference between being able to have the bearing balls go over the hump and having enough play so that it moves along versus getting bound up. And the more tighter you tolerance that bearing and that gap, the straighter lines you will travel, but at some point it begins to bind up. And so you typically need some way to adjust that. When you're designing a bearing, rotary or linear, you need some way to adjust your preload. If you go to a wheel bearing, for instance, on your car, one of the things they do when you first put in the bearing is you put it all together and then there's a nut on the end. And there's a specific procedure to, you spin the wheel and you tighten the nut until the wheel comes to a stop. And that meant you have too much preload. And if you ran it there, your wheel would heat up and basically explode from heat because it would be too bound up. And those balls would be you're deforming ball bearings and they'd be creating so much heat due to deforming the balls that there wouldn't be any play in that wheel. That wheel would be rock solid, but it would have a lot of friction. So then you back off the nut a little bit and, oh, now I got a little bit of play in the bearing, and it's up to you to decide do you have too much play and the thing rattles around and your steering is like this, or you don't have precise motion, and when is it too bound up? So when you do bearing design, you have to decide some way to adjust preload. The more precision your surfaces, when you start to get surfaces like that you made with a lathe or machine tool surfaces that are down in the tens of thousands, really good machine tools, this becomes way easier to adjust because you don't have the variations in the surfaces. So preload kind of depends, but almost all bearing needs to deal with it at some point. And so like in this bushing, you would have this thing we would put in a thing right here, and that would be called a gib. And then you would have some, and we actually physically do, if you look down on the side of this, you will see, oops, I've lost a nut, but you will see set screws right here. And those set screws, did my camera go away? Uh-oh. We have along this side here, there's 4 set screws, and those come in right here. So when you put this in with these little divots, this would go in like that, and then this would get assembled. There we go, like that. So now we would have a bearing, sliding friction, adjustable preload. That's good. Adjustable, we could set these in. So why would you ever want to do this? This is a pretty common device in, for instance, manual milling machines, drill presses, where you clamp tools together, or you would have you can see on the end, this has a hole, and that hole is where you would put in a screw mechanism, and so you and set something. Why would you use something like this with the sliding friction? You would generally use it to set a position, but then the great thing about this bearing is think about the loading that you would put on it from here. This bearing can take a lot of load because of the structure of it, but it also can take impacts. So I could get out a hammer and I could bang on this thing. In fact, do I have a hammer? See, I should bang on this. What kind of YouTube video doesn't have a hammer banging on it? I'll bang it on the table. How's that? There we go. So you could take something, this could take loads on it. For instance, if you did a punch press and you were punching out something, if you had little ball bearings as your bearing material in here, every time you had a punch operation, you might be Brinelling those bearings, taking those little ball bearings and kind of pounding them into the bearing surface and giving the surface little pits, so to speak, where it made little divots. And this kind of thing could take repeatable pounding and impacts, but you have, the best you can do is lubricated steel on steel, which is 0.23 or something like that. And with light loads, this moves back and forth pretty nice. I can move it back and forth with one, look at this, even my pinky, I can move it back and forth, right? It doesn't take much force, but as soon as you load it down and you put, now you can barely move it. And that's just even with a few pounds because of the coefficient of friction. So worthwhile talking about there, this is why though, we are moving towards rolling elements instead of sliding elements. Okay, so done with that. Any questions on the dovetail?
I have a question on the preload.
Yeah.
For a rotary bushing, is the only way to adjust the preload to machine out a little bit more of the inner diameter?
No, you could use heat and cold, to control dimensions. Anything that you can think of to control dimensions is what you're after. So in general, yes, you're going to have to think about, could you use a taper fit and tighten it so that it's got a slight taper? That's adjustable then. If you just had one size shaft and one size bearing and had them go together, it's going to be very temperature dependent, especially if it's anything but steel. There's a reason you don't use aluminum very much around bearings, is because aluminum expands, coefficient of expansion is about 3 times that of steel. And so aluminum changes its shape badly compared to steel. The stages that I'm going to give you tomorrow are a steel structure. This one here that I've been showing here, this is this one, oh, that's steel right there. This is all aluminum around it, bolted on the round, but when it comes right down to the very bottom, that's steel, my new magnet. And they use steel with the bearings because everything, then the ball bearings, the housings, this plate, all change at exactly the same rate. So that's why the first thing I said was temperature changes. You could change the preloading with temperature, but that's not a very predictable thing to do. So wait,
so how do they deal with the changes in aluminum frames of aircraft?
Yeah, well, it's a problem. I don't know if you ever heard an aircraft creak and groan as it's taken off, and like, what's going on here? It's because it's changing, and they have to do something to adjust for that. And one of the things they do is they skin it with aluminum, but the structure might not be aluminum. The structure might be more titanium. It's a huge thing when you're designing something like that to constantly be looking at when the temperature changes, what dimensions changes and where. Some are a problem, some aren't a problem, right? I remember back on the farm, we had hand lines and wheel lines. You guys know what those are? Sprinkler lines. You see them out in the fields. You see these long sprinkler lines running, the whole quarter mile long of sprinkler lines. And irrigating pastures or whatever. And I remember it'd get really hot in the summer, and you'd look out at those aluminum lines that were all connected together. If they left them connected together, and instead of being straight, they'd be S-ing through the field, because the aluminum expands so much that the only way is if it was no longer straight. It was a big curve. I mean, we're talking 20, 30 foot deviations out through the field with this aluminum structure. And it just jumps out. It's like, wow, that really has a coefficient of thermal expansion, doesn't it? That's not what I said there. But after engineering school, that's what I said. And so it's just a thing you got to deal with. I mean, I always thought about aluminum heads on your engine. You know, you got a steel block and an aluminum head. How do you deal with the gasket material that'll handle the expansion on the aluminum right in the hot spot? It's difficult. It's difficult. And if you can make it work, great. And eventually it doesn't work and you blow your head gasket. And, you know, there's some engines that, like the Toyota V6, it's so predictable. You hit 80,000 miles and your head gasket blows, because it's expanded, contracted, and that's the life of it. And every time it did that, your tolerances changed. Linear motion and motion control machines generally don't have huge variations in ambient temperature. The temperature comes from inefficiencies. So one of the things that you're going to pay attention to, for instance, like this, when we get to the drive mechanisms, this is a ball screw and it's highly efficient, like 0.95, meaning when you have an efficiency of 0.85, 0.95, that means that 5 to 15% of the energy that's going into it is getting converted to heat, and the rest is used as mechanical energy. When we go to a friction type of nut, like we would have in something like this. This is a Acme screw in here, and it's a sliding friction, or a simple bolt and a nut is sliding friction between the nut and the bolt. And we'll get into these threads, but that efficiency is down around 0.4. Instead of 0.9, it's 0.4. And so all the heat generated in a nut, and you know this from if you've ever taken a nut off of something and had to really wrench on it, and you grab the nut when you're done, it's like, oh, the nut's warm. It's because there's a substantial amount of energy that went to heat that from what you